I know that the last
Yeah,
so I guess I was glad to see that it's not as big as
yeah, we gotta
when I
get,
saw the zero, I was like 50%.
oh, it's not weighted as much.
So once he recreated
So it's not 50%, the exams aren't 50%.
I don't know like what they are together. But I mean you gotta also think like you got higher than 50% of it.
Anyway, we gotta keep our projects.
Yeah,
We gotta keep maxing those
when I
out.
saw the zero, I think I had like 56% of this class with the homework compilation.
I didn't even see it when,
Yeah, it was.
I saw it
really low. So, I mean, you could go put a zero. See what it was. So, yeah. But then I was that was my bad too. I was looking at the code in that we figured it out. That actually was code that it was actually was. So we did great.
You can grab your paper if you want. You need to hand in later. So if you want to grab your paper to take a look.
thank you.
Do you still want?
Sure.
Still, you need to hand in. Alright, so
And then we got a zero.
so let's get started. At the beginning of this lecture, we will go over the midterm test. If you have any questions about your grading, if you have any concerns, please come to the office hour or make an appointment later. We'll do whatever we can to make it right, okay? And also, since I think one of the questions we used this year is, sorry, we won't be able to distribute all the papers to you now, but for anybody who hasn't got your papers, please come to us later so that we can start now, okay? But you can always come to the office hour and also make an appointment to come to see your paper and express any concerns you have. So I think one of the problem here is the part 1, question G in problem 4. I think that's a little bit tricky to handle, so almost nobody got it. Most people only get 1 point, and very few get 0 points, and also very few get like 6 or 8-ish. So if you get a 6 or 8-ish, you are doing really good on this. So anyway, so due to that, this is actually something I added this year. So I didn't think that it was so hard. So because of that, the average is significantly lower this year than last year. So we will do some adjustment to the score. So don't worry about that. We will probably raise the average to 73, 74-ish. So that means adding about 13 or 14 points to your actual score. Okay. But that's just to kind of for the question G in part 1, part 4. Anyway, so but that will be done a little bit later after you have expressed all your concerns about gradings, and then we will decide the actual number of points to add. Okay. So I'll first quickly go over all the questions. So if you have any questions about the solutions, please let me know. Okay. So can you see that? Or is this better? Okay. So the problem 1 and 2 are pretty standard. They are basically relational algebra and SQL, and that involves the basic 5 relational algebra operators and something like the divisions, right? And also renaming you want. Also, in the SQL part, it's basically some implementation of this simple and complex operators. So, if you have any questions, just let me know. But if not, then I'll just skip this. Okay. Therefore, problem 3, the first question, I think at least half of you have done this right. Actually, this is not hard. The trick about this question is that you only have 1 main memory frame. That means whatever eviction policy you use, that doesn't matter. Okay. So whenever you are accessing a new page that's not your buffer pool, you need to evict it, and you only have 1 choice. So the eviction policy doesn't play any role in this question. So the solution to that is actually, so since you have 100 distinct page IDs, so if your 10,000 access is arranged in such a way that all the access to the same page are consecutive, then basically you only pay 100 IOs, right? And the best case would be, that's the best case. And the worst case would be every access is access to a different page than what's in the buffer pool, okay? Then you get 10,000 IOs, so that's the answer, okay? And question 2 is almost exactly the same as the homework, so I won't go into the details about that. Then for problem 4, the first couple are pretty standard. So a common mistake you could come up with is here. if you do not subtract the header size from the total page size, that's one potential issue. The other one is to notice that here, here, in this question, when you're calculating the tree height, the bottom level is called leaf pages. They are not internal pages. So basically, in our specification, we say 80% for all pages in data file and say 70% for all internal pages in the index. So that means the leaf level also has an 80% utilization ratio. So that's basically about it. And also notice that it is alternative 1 instead of alternative 2. That means basically you embed the whole record in your leaf level. And typically that means, so actually there are two approaches. One is you extract the key out at the beginning of your actual data entry. That's a possibility. If you do it that way, I should have give you full credit. But you get a smaller answer than, you get a smaller handout than this. But that's fine. Another better approach is you optimize out the key field. In that, you basically just use the record itself. Because the key is in the record, you can always access that if you reach some of the data entry. That's also a possibility. So that's, here the answer is for that. For E, this query, there are several things to consider. So basically, this RID is the primary key in your schema. So basically, if something is a primary key, then it's unique in your table. Every record has a unique primary key, right? So since it's unique, and you know the range is from 0 to 10 to the power of 8 minus 1, right? So that basically means this range is basically the higher end minus the lower end, and that's plus 1. That's the number of records. So if you treat this as the lower end is inclusive and the upper end is exclusive, that's also okay. I also didn't deduct any points for that. But that's one thing, first thing to consider. So that basically gives you 2 times 10 to the power of 7 records to scan. And then, so how many pages you have is basically you divide that by the number of records per page. Then you plus 3, which is the tree height, which gives you, so initially you do a search along a tree path to reach one of the data entry. Since the data entry is the record itself, here you got alternative 1, then you just scan them sequentially until you reach the end of your range. So that basically gives you the number. And for F is trickier since this ratings is the index is not on ratings, right? The index is on RID, so you cannot use the index. If you use the index, of course you can, but you might end up paying a higher cost, right? So the best thing to do is simply scan the data entry level or scan the heap file. So that's why you just end up with a number that's equal to the number of data pages you have in the database. Okay, and G is really tricky because here we didn't ask for IOs, number of IOs. Instead, we asked for running time. Okay, to compute the running time, you have to take into consideration the type of IO you are using. So basically, random IO and sequential IO, the difference, the speed difference between them makes plays a role in this question. So here, actually the best solution is 3, right? Is 3. If you just embed this RID inside your key, then whenever you use this index to scan the data entries, you do not need to fetch the actual data record. Okay, so that's the fastest. And 2, if you just have an unclassed index on ratings, that's actually worse than if you just scan the heap file. Okay, why? Because in class we talk about how bad the random IO is. Actually, I engineered the numbers here so that I think 2 and 3 have roughly the same amount of IOs, but for one, it has a higher IO, but it's just less than, I would say, 10 times. It's about 5 times. But given that random IO is slower than sequential IO by at least 10 to 20 times, so that means basically 2 will be slower than 1. Okay? So that's the trick about this. And finally, they're just proofs. So they're standard proofs, and you can see that in the lecture slides. So for 2, actually, we were quite lenient on giving the points, actually. So if you mention Pigeon's-Hole principle, even if you do not have any arguments about that, to give 5 points. If you can give a reasonable proof, although maybe with some small loopholes, then maybe almost 10 points. And if it does make sense to us, then it's 10 points. Okay. So that's it. So if you have any concerns or questions about your grading, let us know in office hour or send a point. So we will adjust whatever it takes. Okay. So that's about the midterm. So for those who haven't got your paper, you can come to the office hour later to grab your paper to take a look at it. And for everybody who have taken the paper here, please hand it in after this lecture. The reason is that because a lot of questions are gonna, I would say, are gonna appear in next year's class, so we don't want to have a record of that. Okay. But anyway, that's about it. So let's continue from where we left last lecture. So in last lectures, we gave a simple overview of query evaluation, what's the process of query evaluation, and we gave a preview of the simplest possible query, which is single table query. And so basically the most complex single table query you could come up with is something like this. You have all the possible clauses, except that the from only has one table. And for this, basically, you can come up with some kind of data flow model, which is called Volcano model. And each node in this diagram is something called an iterator. And an iterator will have an interface that looks like this. So basically, the downstream operator will repeatedly call next on its input to get the next tuple. And depending on what kind of iterator you have, whether it's blocking or not blocking, you will have different internal states, and it will decide whether it passes the process tuple on the fly or store it, then process everything, right? So we gave an example about distinct. Distinct is here the distinct because it works on the sorted data, so it's a non-blocking operator and it works on the fly, right? You just compare the current tuple to the previous one on its key column. If they match, then it's a duplicate. You just skip this one and fetch the next tuple. If they don't match, then this is a new tuple. So you basically return this tuple. Okay, this is distinct. And then we talk about sort by, and an alternative to that is use a hash table, right? So if your hash table fits in memory, that's good. That's easy. But if not, then you need to do a partition, then rehash that, right? Partition basically partition the whole data set. Although it's larger than your memory, you utilize your memory to partition it into a bunch of small partitions of disks. Then you get a reading each of the partition one at a time and rebuild another hash table using another hash function, HR, on that as an internal memory hash table. Then you perform all the grouping of that, or distinct, right? And also we talked about what's the maximum size of the table if you can do this in one pass. One pass means you only need to partition everything once, right? So if in the case if you have a larger partition, you end up with some larger partition than your memory, then you need to repartition that particular small partition into smaller ones so that they fit in memory, and you recurse on this until you get every partition that you get every partition to fit in memory, right? So we talk about what's the maximum size of the table you can end up with if you want to do the whole process in one pass, which is the answer here, n times m over b times m over b minus 1. And also alternatively, you can say that if you have a data file of size n over b and assuming a uniformity, then you only need square root of that space to do the hash listing for that in one pass, right? So yeah, then we end here. Basically, we only gave intuition of what's hybrid hashing. Okay, so let's continue here. In the last lecture, we talked about if our data is larger than your memory, but you do not want to pay the full cost of like hashing everything to disk then reading again, right? Or your data is actually smaller than your memory, but you do not know that fact, okay? Until you actually execute the query. So if that's the case, you can do it in a more graceful way, like this. So basically, you keep the first partition entirely in memory and immediately build a in-memory hash table using the rehash function for that. Then the remaining of the partitions are still dumped to the disk. Okay, so for the first partition, because it's already maintained, so a hash table, in-memory hash table is already maintained on the first partition. So you can immediately get all the answers you want for the first partition. But for the remainder, you still need to read them in later to build internal hash tables to produce the final result, right? Well, one thing to think about the intuition here is that if you just blindly use the partition hash function to partition the data, you could end up with a smaller partition than your available memory, that in-memory portion of your hybrid hash, right? So it could be the case that your first partition is so small that it only occupies half of this memory, right? Then why would you do this, right? So how can we improve that? So to improve that, we actually define a new hash function called h of h. So basically, given key k, h of h will equal to 1. So h of h k will be equal to 1 if k fits. Sorry, there are two possible cases. If k is a new key, that means it's never seen during your prior execution. So up to this point, you see a new key k. It's not existent on your previous data. Okay. So if k is a new key, then this is okay. Or k is not a new key, but since k is not a new key, right? So, but k is existent in the in-memory hash table. Okay. So basically, that means k is k exists in partition 1. Okay, it's already there. This is a slightly strange. Hash function because it actually depends on the order of your execution. Okay. Oh, by the way, so if it's not, then basically you just add 1 to the original partition hash function. Okay. So basically you end up with this HP is from the domain to the range. If this function maps from domain to 1 to m over b, then this HP will map the domain to 1 to M over B minus 1. Okay, just if you choose the partition function, you just make it range 1 less than the full size of the memory. Okay, so basically this function is a little bit strange. Basically, you assign partition the hash value 1 to assign a value to a partition 1 if it's in memory. Okay, if it's a new key and if it's in memory, if it's in your the K buffer hash table portion, then you just declare the hash value of that is 1. Okay. Otherwise, if the K is not a new key, that means you've seen this K before in your data, but also it's already in that K buffer hash table. Then you also declare its hash value is 1. And although this function is not deterministic, right? This function is actually not deterministic in the sense that if your data are ingested in different order, you can produce different hash functions, hash values. But you can convince yourself that for a particular input in a particular order, you always produce the same hash value for a particular key, right? So that the reason is that exactly the condition we say here, right? If K is a new key, then it doesn't matter whatever hash value you assign it. You've never seen it before, right? But if K is not a new key and it's already in your first partition in the in-memory hash table, then you don't have a choice. You still need to assign a key, hash value 1 to it, right? So as long as a K is existent in this in-memory hash table, it always gets a hash value of 1, right? But in some cases, when your K buffer hash table fills up, you do not have any space there, and you encounter a new key, then this particular condition doesn't hold. So then you default back to the original hash function HP of x, and you get a partition number here, right? So basically that means whatever function key that's not existent in the K buffer hash table, you will redirect that to one of these M over B minus 1 partitions on this partition. So because HP of x is actually deterministic, so you always get the same hash value for each of these additional keys, right? So that's the trick here. So to put this in a more intuitive way, from the view of programming, it's actually more intuitive than the formal definition here. It's just like you have an in-memory buffer pool, and you have spared a bunch of output buffers for additional partitions to spill data that doesn't fit in memory. Okay, so whenever you have a new element, whenever you have a new tuple, say key, and you extract the key of that's K, right? So K is the key of this tuple key. Then you probe the K buffer hash table with this key K. Okay, if this K is there, then you basically just maintain whatever thing you need to maintain in that hash table. Okay, so basically, if you are doing a group by, then you just maybe add the count or add some values to the sum or maintain the average. That's about it. But if this K is not in that hash table when you're doing the programming, then what you do is that you check whether this K buffer hash table still has some space. If there is space, you still put this K as a new element into this hash table, and you initialize all the counts, right? Then what you do? Then you're done with this K, right? Another case could be that the K is not in this K buffer hash table, and this buffer hash table is already full. You don't have any space there. what you can do is basically use another hash function HP of x to dump it to one of the spill partitions. Okay? So only when your memory is large enough, you cannot fit a new key into the in-memory hash table. You spill that particular tuple into a external memory partition, spill partition. Right? So that's the view for programming, and it's quite intuitive than the mathematics here. Right? Okay. So that's about it. Of course, so for the k-buffer hash table, in-memory hash table, you always have to choose another hash function other than HP or h of h. That's called h of r, the rehash hash function, so that it can be hashed to different values inside this in-memory hash table. So basically, this whole thing is partition 1, right? But all of them will have the same hash value of the h of h, which is 1, right? But you use a different hash function called hr, the rehash hash function. Then each of them will have different hash values. Then you can build an in-memory hash table for that, right? So in this way, you can effectively or efficiently maintain those key value pairs, right? You have a key and its corresponding aggregates. So that's how you do it. Yeah.
You had a question in the previous slide on how to choose k. Do you just want to choose k to be as large as possible so there's only like a couple of spins?
Right. So this is actually depends on your data, right? Or your configuration. So I think typically in real database, your memory is not as tight as what we shown here, right? You always have some spare memory. So basically, I think the k should be chosen such that it's reasonable for a moderate size of your data. That actually depends on your knowledge of your workload, right? If you know, on average, your data has only say 10 distinct keys, right? Then you only need enough space for these 10 keys. Then maybe you multiply that by a load factor so that it's slightly larger than that, and you get a balanced buckets, right? Then that's enough, right? Or for a more generic setting, I would say you keep large enough in-memory hash table so that for a moderate size data, you can always do that in memory. You only resort to the spill partitions when your data is too large. Okay. That's a reasonable choice. Any more questions? Yeah. So that's about it. So right. After you are done with the in-memory hash table, basically you've already maintained all the aggregates in one over there. Then, since you still have a bunch of spill partitions, you bring them in to memory one at a time and build another hash table over that, and using the HR rehash function. Okay, and then you can get all the data by aggregate results. Okay. That's how we do this using the hybrid hashing. Of course, when you're using hybrid hashing, you could still end up with a case where you need to recursively apply the hybrid hashing on that, right? So if your data is extremely large, so that you have processed some in-memory portion of that, and you have M over B minus 1 spill partitions, then you bring in one of them at a time, but that particular one is still larger than your memory. So you're still gracefully using this hybrid hashing technique to process part of that data purely in memory, then spill the other portion onto disk. Okay, so then you end up with more partitions, but that's smaller, and in the end you will process everything. Okay. No? So that's about hybrid hashing. Right? Any more questions about this?
So how do you choose what hashing technique to use, like hybrid or just regular rehash?
Oh, I think typically you just use hybrid hashing. Yeah. But it could also be like somebody is lazy. He doesn't want to take all the complexity here. You can still implement the patching technique. Yeah. So the next to come up is called query optimization. So what's query optimization? So basically, if you have a query, you have many different ways to actually implement that, right? At least for the group by, you have sort group by or hash group by, right? For hash group by, you have this partitioning and rehashing technique, right? Also, you have the hybrid hashing. They all have different costs in terms of CPU, I/O, or many different metrics. So, in order to get the best plan in terms of the metric of your choice, yeah. So typically, we only care about running time, right? But running time is a little bit hard to estimate in a database system because you have different types of I/O, you have different numbers of I/O, and for in-memory data, you still have different CPU costs, right? So it's kind of hard to estimate. So a naive approach is actually to come up with some kind of model to quantify the final running time in terms of number of I/Os or the number of CPU instructions or some approximation of that, right? So the query optimization basically is given a particular metric of your choice, then how do you find the best possible plan for this particular query, right? So that's actually, even for the single table query, it's not quite easy. It's a much harder problem when you have multiple tables, when you have joins. But even for a single table, it's still not a very straightforward answer. Why is that? Because when you are doing this, say you have different operators here, right? I have a right. So typically for a single table query, you always need to get the data through a scan, right? So the scan could be done on the heap or on the index. Or alternatively, if you are fortunate to have a sorted data, then you have a sorted scan, right? So those are different possibilities. But they are actually associated with different costs and different end results, right? So for a heap scan, typically, the cost is, you can assume that it is sequential I/O, right? Typically, if you are just loaded the data onto a disk, then everything is stored sequentially. Then you only pay sequential I/O cost to scan the whole heap file. But you cannot apply any predicate to that unless you actually fetch the record, right? So you cannot just specify a range. Say you are doing just like the example we used in exam. You cannot on a heap. You cannot specify the rating of 1 to specify that range, and you only fetch that range from the heap file. That's not possible because everything is not in order. You have to scan everything and apply the filter ratings equal to 1 on top of that, right? So that's the inherent cost of a heap scan. On the other hand, so if you have a cluster index, you can do it. You could potentially do it better because you can search for a particular range, say ratings equal to 1, then sequentially scan every data records of that, right? Or if you have an unclustered index, one thing that you could do is you can still use the index to reach a particular data entry and do an index scan over the data entries. Then, if you want to access something that's not in the data entry, then you need to fetch the actual data record from the heap file, and it's potentially random I/O, right? So that's just something you might need to consider, right? So depending on how many IOs you are actually using, so how many IOs you are these two operations actually require, and or the relative speed of random IO and sequential IO of your hardware, you can come up with totally different costs, right? So that's something to choose. And then you will need to apply any wear cost, the filter, right? So for filter, actually, there are two. So here it seems it's irrelevant because you can always apply everything with flag, right? You can just whenever you use the scan operator emits a particular tuple, you apply that filter on top of that. If it passes the filter, then you return that tuple to downstream. Otherwise, you basically skip that one and fetch the next. But in reality, there are actually multiple other choices of how you actually apply the filter. There are strategies of that. Okay. So because in a real database system, everything is layered. You have different layers. You have access methods. You have query engine, right? So that's actually a heavy boundary. There's a heavy boundary between them. Whenever you are passing something, potentially you'll need to do some translation, or you need to pass a pointer. That's okay. Or in certain cases, you need to copy the data. So those are something you need to consider, right? So in that case, if you apply the filter on the fly, it actually might not be the best possible scenario you might want, depending on the particular scenario. So yeah, that's also something you might want to consider, right? So for example, if your filter is so complex that, say your filter is a machine learning model, and it has so many, it's a deep neural network, and you have so many parameters to use to produce a prediction result over a particular item, okay? And since your parameters are, the number of parameters is so large that it occupies a very large amount of memory, then what happens is that you could mess up with your cache, CPU cache, right? Whenever you apply this filter, your CPU cache is filled with the parameters of your model instead of the actual data. But in reality, if you are doing a heap scan, you fetch a page into your memory, then potentially, because you are basically accessing those records sequentially in memory, your CPU could do some prefetching, prefetch that into the cache so that it actually performs faster than you fetch one, then do a complex filter of that, mess up with your cache, then CPU go back to the memory and then refetch that tuple from memory to cache, right? That's something to consider in certain cases, right? But in a traditional sense, that's not a concern because the disk is already flexible. And then potentially you could have a group by, right? For group by, you could use the hybrid hashing we mentioned before. So that's the hash age aggregation operator we show here, right? But that's not the only option. You could also do a sorting, right? Depending on how large your data is, it could be sorting is faster than this hash, right? That's also a possibility. Then on top of that, you have another filter, that's the halving clause. Halving clause applies to the groups you have produced. So that's another filter, right? So you still have the same kind of problem, how to actually implement the filter, whether you push the, whether you do batch filtering or you do filtering on the fly, or alternatively you could also push the filter down the query tree, right? The query plan here. You could push some filter into, say, hash aggregator, or the downstream filter or heap scan. Right? Those are all possibilities. Then finally, you have a sorting, right? For sorting, of course, you need to decide whether your data is small enough so that you can do an internal memory sort, or it's so large you need to do an external sort, right? Those are basically all different choices. And where did the select clause go? It's implicit, right? Because when you do a select, you can basically apply that on heap scan. when you are fetching the records, you do not actually need to pass everything to downstream. You can basically immediately do the projection. As long as everything you need is still retained there. So if you push the projection operator through everything here, you probably need to add additional columns that appears in the filter but not in your select list. That's the possibility. Right? Okay, so that's basically the quick overview of the query optimization of a single table.
I have a question.
Yeah.
And you said that you'd add those columns because of like count and max and things like that you can add in
Right.
to the select statements.
Yes, you could add that. So those parts will appear depending on whether you do a group by or whether you do a group by or not. If you do a group by, then those will be added here in the hash aggregator. If not, then you will have an operator called ATT, something like that. That's a single aggregator of all the data. Okay. So actually, in reality, people tend to combine these two operators, the hash ATT and ATT. Okay, because basically the hash. So basically, if you do not do a group by, it's essentially grouping by of one, right? Any same, the same value, right? So they can basically combine them. So that's the summary for everything we talked before, in last lecture and this lecture. So basically, we talked about single table query, how to execute that, and how to optimize that. Just gave an overview of that. Okay, and we also shown hashing is a powerful alternative to sorting. Like you could use that for group by or district. Okay. So the next thing is that we actually need to formalize everything we talked before. How do we actually reason about the query execution and optimize that? So that actually comes down to the relational algebra. So basically, in a database, you can think of that, although this is not exact right, but it's, I would say what they do as a plan is a superset of the relational algebra. It's more complex than the relational algebra, but the algebra is the core of that. Okay? So basically, you still end up with a bunch of operators that you need to consider how you actually optimize that. How do you rearrange or come up with equivalent relational algebra to execute the same one? Okay. So let's see. Let's still use the example we've been using throughout the semester. So basically, you have a sailors table where the SID is the primary key and you have a bunch of other columns, and you have a reserves table which encodes all the data that a particular sailor books a particular boat on a particular day, and that's the primary key, and you could also have some other columns. So let's suppose still the same stats. So each the reserve, each of the reserve record is 40 bytes long, and there are 100 tables per page and 1,000 pages in total. Right? For sailors, each record is 50 bytes long, and you have 80 tuples per page and 500 pages. That's about the stats. Okay, we will show how we actually use this method about your database. So let's see. Let's see this. This is something that's very simple, like the selection relational algebra operator is actually equivalent to the where clause you typically use in your database, or it's the having clause on top of the group by results. But anyway, that's the filter, something we call a filter or selection predicate. So then it's typically in the form of this. This is actually a simplistic form of that because it only allows you compare a particular column of your record to a particular constant value. But in reality, actually, so for single table, you don't have multiple tables to prepare, but I don't know. In certain cases, you might also want to compare two columns, right? You could do column A is greater than column B, something like that. It's also a possibility. It's not something prohibited here. But for simplicity, let's assume we have a predicate that looks like this, right? It's some column with some op. Op is something chosen from smaller than, greater than, equal, or not equal, something like that. Is some kind of operator. Or if it's a string, you could also have like, right, to do the matching. Right? So then, given this selection predicate, if we have a query like this, how do we actually choose the filter implementation or the scan implementation, right? For example, suppose you have a heap file on the entire table R, and also you have a index, say it's a B plus tree index on the R name column of R. Okay. So what's the alternative here? Right? You could you could use either of the index to do a scan, right? So for heap file, basically you scan everything and try to see whether the R name column is like C, if it's starting with a C letter, capital letter C. Or alternatively, since this is C percent, so that means this particular predicate will match all the strings that starts with a capital letter C. Okay, so if you have a B plus tree index or R name, the alternative is to search for the lower range for this particular string C. Right? So you just find all the R name that's greater than or equal to this particular string C. Then given the lexicographical order, everything that matches the like C percent will be after this particular data, right? So then you could also use the B plus tree index, right? If you have a hash, what about a hash index? If you have a hash index, what happens? Can you use that? No, right? Because everything, although every string there's an order between on all the matching strings and C, right? But they don't necessarily have the same hash value, so you cannot use the hash table. So that's useless. Okay. So then we define a terminology called reduction factor, or alternatively, you can also call it the selectivity, which is the percentage of matching records to out of your entire data. Okay. So suppose my data look like this. Suppose my data look like in the R name column, I have A, B, A, C, 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 D, and D, E. Alright? So the selectivity is defined as the number of matching records, which is 2, divided by the total number of records, which is 5. Okay? So that's the selectivity. So this selectivity actually gives you a lot of important information of your data. Actually, so because this selectivity is to be estimated instead of query, right? Because here you are basically trying to optimize the query. You cannot execute a query just for like estimation. That defeats the whole purpose of your optimization. However, that's not essentially like necessary too in nowadays database research. There are some work that does continuous optimization, like you can feedback some new statistics on the fly, but that's not our concern here. We just talk this in a traditional sense that you only do the optimization optimization once, right? Then you execute whatever plan you come up with. Then you don't actually have a chance to execute a query to estimate what this reduction factor or selectivity is to get the actual cardinality of your output. So then you will need to actually estimate this selectivity based on your statistics, based on some kind of statistics you might maintain in your database. Okay. So that's about selectivity. Of course, here the examples are the different cases what we talked about before. Here are some actual costs you might want to compute when you are comparing different methods of scanning a table. For example, here with no index, unsorted, which is exactly a heap file, right? You only have a heap file. So essentially, you must scan the whole relation. So that cost is actually m. This m is the number of pages in R, right? So if your cost is only covers for only counts the IOs, then it's the number of pages here, right? It's 1,000. So if you are using a heap file to scan the whole file to execute the query, then your IO cost will be m, just 1,000 IOs. And then if you do not have an index, but this heap file is actually sorted, so this corresponds to a sorted file. So the cost of that would be doing a binary search, because everything is still sorted. You can do a binary search to search for the lower range of everything that's greater than what you see, right? So you could do a binary search for that. Then you need to scan everything that satisfies the containing results. So that basically is log to 1,000. That's roughly 10, right? You take 0, that's here. And for the second part, it's a little bit trickier. It's actually the selectivity times the number of pages you have, right? So that's where this selectivity comes into play. So basically, if you can estimate the selectivity accurately, then you can know what's the number of IOs you pay for a sorted file, right? That's the role of selectivity. Then, what if you have an index on selection attribute? If it's hashed, then we've already said that it's no use, right? The only thing that's useful is B plus 3. Okay, if you have a B plus 3 or R name column, then you could use the index to find the corresponding data entry, right? Then the cost would be something like log B. B is the fan out. All right, let's use an F. F is a fan out. Then log F of 1,000 and take a city. That's the cost to reach the first data entry on your B plus 3 that satisfies the predicate. Then you plus the same thing. So basically that's selectivity times number of pages, right? But however, there are more stuff to think about. What's the number of pages here? It actually depends on what kind of query you have, right? So let's see this. What's this for? This is a select star query. So you are asking for the actual data record, right? So if you have a cluster index, then it's fine. You just go into the heap file and start scanning everything there, right? But you have an unclustered index. This is potentially huge, right? This is no longer selectivity times number of pages if you have an unclustered index. It's selectivity times the number of data records you have, right? That's significantly large. Okay. So that actually depends on what kind of index you have. So that's exactly what I'm saying here, right? So let's see this example. So basically, suppose 10% of the tuples qualifies the selection predicate. Our name is like C. Our name starts with a C. Then with a cluster index, the cost is just a little bit more than 100 IOs. So basically, for a 1,000 page, maybe you only need height 2, B+3 with of height 2, right? So that's basically you just pay 2 IOs to go to the corresponding data entry, then just 100 IOs to actually fetch those data records, and you're done. That's the cluster index. If you have an unclustered index, then potentially it could be up to 10,000 IOs, right? Why is that? Because you have 100,000 tuples in total, and since the selectivity is 10%, you are basically scanning 10,000 records. And these 10,000 records has been fetched individually, and each of them potentially is a IO. Okay. So that's the cost. And also, right. So here's some analysis of how many tuples you will have. This is quite interesting actually. This causes a lot of trouble to us if you want to do some fancy stuff like sampling. Really, it's really fancy. No, sorry, really bad for purpose of query evaluation. Like if you assume uniformity in the selection column, then what's the probability of a page is fetched? Okay, so here the page refers to actually the key file page. Okay, so if you assume this all your data that starts with a CER name is uniformly distributed over all the data files you have in your key file, then what's the probability that the page is fetched? You can think about that. Actually, so you can think of if you assume uniformity, then basically you can think of every tuple in a page has a chance of 10% to be selected, right? So the probability that the first tuple is not selected in a page is 1 minus 10%. That sounds large. That's 90%, right? However, you have 100 tuples per page. So that gives you 1 minus 10% to the power of 100, right? That's extremely small. So the probability that you don't choose anything from a page is extremely small. So that's why you almost always fetch all the pages as long as your selectivity is moderate. Actually, so I've done a lot of research on this. In my experience, so on some like on a typical benchmark like TBCH, on the line item table, if your selectivity is around 10 to the minus 5, right? 10 to the minus 5, that's 0.001%. If your selectivity is that low, then you could potentially get 10 times higher performance on unclustered index than you scan the whole file. If your selectivity is 0.01, 10 to the percent, or 10 to the minus 5, then it's roughly the same as scanning key file. And as long as your selectivity is higher than that, it's bad. Yeah.
Do databases try to have like data that's somewhat similar located in similar pages in a heap file to mitigate this kind of problem?
Right. So I think database should make effort to do that, but in reality they don't. Okay. So if you load a file into your database, it's basically typically it's stored in the same order as you give it. So that actually depends on that. Right? Okay, that's about using an index for selection. And this is where your selectivity might come into play when you are estimating the number of IOs you would use using different indexes, right? So that's it. So one possible refinement with unclustered index is that you first you make a blocking of it. What you do is that once you reach here, once you reach the data entries, say the first data entry is here, instead of directly getting the corresponding data records in the heap file, no, you start scanning the data entries until you reach the end of the range. Okay? And then you get a bunch of data entries, out of which you get a bunch of record IDs. Then what you can do is actually you sort these record IDs according to their page numbers, so that each of the unique page number is, unique page is only accessed once. Okay, that's a possibility, but that actually, so for a typical database, this is practical only when your data is not too large. Okay, I would say maybe 100 gig is not too large. A terabyte, maybe. 10 terabyte is definitely too large. Okay, because why? Why is that? Because the data entries is actually actually the record IDs are much smaller than your actual table. So maybe say for TBCH, for the line item table is typically a factor of maybe 10, 4 to 10, I would say, depending on whatever what record ID you're using, right? So that gives you actually a significant reduction in the data set, right? If you have 100 gigabyte of data, then if your actual data record is 10 times in size of the record ID, then you only end up with 10 gigabytes of record IDs at most. Then 10 gigabytes can be easily fit in memory, actually. Or if you have also typically if you use a particular unclassed index, you have some kind of selectivity. So you won't end up with the full data set. So that's why you could end up with a significantly smaller set of record IDs than tuples. Then what you could do is basically store all the record IDs in memory and do an in-memory sorting of that, and that's cheap. After that, you sequentially fetch the records. Okay. So that's a refinement. Okay. So we talk about the single selection predicate that's in the form of column of some value. Let's consider a more general case. What if we have a general selection predicate like this? You could have a predicate on reserve, so that the day is earlier than August 9th, 1994, and the R name is Paul, or the bonus ID is 5, or the SID is 3. Right? That's a weird part. So how do you actually estimate the size of output or selectivity? Right? So first, you can convert this into a conjunctive normal form, CNF. Right? So a conjunctive normal form basically looks like this. So for each of the bracket, you have a bunch of atoms. Okay, of there, each atom predicate is basically in the form of column of some value, and they are connected by OR. So basically, you have to have column 1 of value 1, or column 2 of 2, value 2, and so on. They are all OR, they are connected by ORs in the bracket. And between bracket, they are connected by N. So basically, you have a bunch of similar brackets that's connected by N. So that's called conjunctive normal form. Okay? Like here, in the example, if you organize the example into a conjunctive normal form, then it looks like this. Okay? It will be days smaller than August 9th, 1994, or port ID equal 5, or SID equal 5, and the other one. Right? So when you're doing that, we only with OR actually the thing gets much more nasty, and you don't have OR. So for simplicity, we only talk about the case where you don't have ORs. Okay. You just have a bunch of column of value and column of value and column of value, something like that. For ORs, it's actually much harder. Okay, but anyway, so if you have an OR for estimation, you could always do like use a union bound or something like that as a safe bet. But that's really good. Okay, so let's erase this. Right. Okay, suppose you have a B-tree index that match terms that is a prefix of the matches the terms involved in this conjunctive normal form. That's a prefix of your search key. Okay, an example would be if you have a condition like a equal to 5 and b equal to 3, that's your predicate. Then it will match an index of ABC, right? But if you give a predicate that is b equal to 3, then it doesn't match this particular index. Why is that? That is because everything that has a equal to 5 and b equal to 3 will be in a consecutive range in your b plus 3 or ABC. But everything that has b equal to 3 doesn't necessarily be consecutive in your b plus 3 if it's all ABC, right? Because you could have 1, 3, 1, 1, 3, 2, 2, 1, 2, 2, 1, 2, right? Something like that. So basically, these 4 are all tuples with b equal to 3, but they are spread around your hash index. The b plus 3 index. So that way, you cannot use that particular index for this particular predicate, right? So this is a matching step. You require the attributes involved in your predicate actually match the prefix of your search key. And for hash index, you don't have any choice. Your search everything in your key of the index must be existent in your predicate. Otherwise, you cannot use the hash index because you cannot actually compute the hash value with missing values. That's the issue. So the general approach to a general selection predicate, our approach is to find the most selective access path, right? So let's see if we have an example. Okay, let's see this example. Suppose our query looks like this. We want day smaller than August 9th, 1994, and both ID equal to 5 and SID equal to 3. So if we use a b plus 3 index on day, then we can basically select everything that has a day smaller than August 9th, 1994. Then we apply the additional filters BID equal to 5 and SID equal to 3 on top of everything you fetched. Okay, that's one possibility. Another possibility would be if you have a hash index on both ID and SID, then you could also use the hash index because both of these attributes in the key also exists in your predicate. Then you could use B equal to 5 and SI equal to 3 to compute the hash and find the corresponding data entries and the corresponding records. And then you can apply the additional predicate, day smaller than August 9th, 1994 on top of that. But there are different costs associated with that, right? So suppose I know this one has a selectivity of 20%, and this one has a selectivity of 10%, right? Then it is very obvious that so basically the search hash index and B plus 3 index won't differ too much. Suppose they are both uncast index. Then basically the fewer records you emit from your index, the better your query will be, right? Because the fewer tuples you emit from the upstream, the field work you will do on the downstream operators. Like to the filters, you process filter data, and for the group by or selection, you also process field data. Then you will have a positive impact on the runtime, right? So that's where you might want to consider what's called the most selective index. You choose the one with the smallest selectivity. Okay? That's something important. Okay. Of course, you cannot use something that doesn't match your index, right? If your index cannot be applied to this particular predicate, then it won't work, right? So suppose you have a B plus tree on R name and date, then you can't use that particular index. Why is that? Because R name is not in this predicate. You cannot. It's not so part of your predicate is not a prefix of the key of this particular B plus tree index. So you cannot use this one. For this one, day and R name, it's okay, right? Right. You can actually use that, but it's a little bit trickier in that. So you cannot do a search for dates smaller than August 9th, 94, and BID equals 5 because they are still scattered around. But what you could do is that you search for this range in the same way as you just have an index of day, right? So then you could apply the R name apply everything else on top of that. Okay. So basically, this one is the same as this one. These two will work the same way in terms of the selectivity. But of course, here in the second alternative, of course, your data is larger, so potentially your I/O cost is higher. But also that actually depends on specific scenarios. So it is not very sure about which one is better, right? And the last one would be if you have an index on day and R name, does it work? No, right? Because your day, the predicate for day is a range. You cannot apply a range query on a hash, right? You must have an equality search. Okay, so that's about it. And so another approach of doing this predicates, so applying this filter predicate for general condition is you actually fetch record IDs for each of your atoms in your predicates. Let's say you have this one, day smaller than August 9th, 94, and BID equals 5 and SID equals 3. Then suppose you have a B plus tree index on day and an index on SID. What you can do is actually you can search for everything that has a day smaller than August 9th, 1994, and apply. You could apply BI, or you could just leave it there. Then basically you get a bunch of RIDs, right? So you get a bunch of RIDs, different RIDs here as the first step, which all satisfies days smaller than August 9th, 1994. Then you do another search on the SID here, using the second index. On the SID, you get another set of RIDs that satisfy the condition SID equals 3. Then you do an intersection over those two sets. Then what you get is actually day smaller than this and SID equal to 3. Then you could potentially apply the BID, or you could apply the BID where you are fetching those RIDs. Those are both fine. So commercial systems often use different tricks to actually implement this. So basically, because the set is a little bit harder to implement, because everything in the set is distinct, right? When you are fetching from an index, it's actually not a problem because the records should be the RAs will be unique from an index. But when you are doing the intersection, how do you do intersection on a general sense? You could use hash, right? You could also use sorting. But that's actually a waste of time because you need to do the hashing or sorting to help that. So basically, you could do that. That's refers to this index jobs. Basically, build index on top of that. But what you could also do is you could use bitmaps if your RIDs is guaranteed to be consecutive. Right? If you know your RIDs from 0 to 10, then you can create a bitmap of 10 bits, and use that as a way of intersection. Or alternatively, you could also use some approximate approaches where this Bloom filter will come into play. So Bloom filter is basically an approximate data structure that serves to do membership testing. So basically, it tells you whether something is in a set or not, right? But it's only tells you the true answer with certain probability that is high. But with certain probability, you could end up with some false positive, right? Let me say false positive, or false negative, or false positive. Right, that's about it. Then this will not apply in a general sense that if you do that, you could still end up with some wrong answers, but that's fine. You can apply the filter on top of that again, right? So that also works. All right. So yeah, let's talk about this a little bit more. So we talk about the filter, the where clause, right? How to implement the where clause. And then the next thing is how do we implement the duplicate elimination, right? If you just do a select without distinct, then you don't eliminate any duplicate. Then every projection is implicitly down on the bottom level of the scan, right? But if you do have a distinct keyword here, then you need to remove all the duplicates in your result. So the issue is to do that. How can you do that? So the basic approach is very simple. You grab whatever output you get from your upstream operators, then you sort them, then you apply the distinct operator we've shown before. Or alternatively, you can also do a hash. Right? So then the cost of that would be, so suppose we have a size ratio. We have a size ratio which is the size of your projection column divided by the tuple size. Okay? And we suppose that is 0.25. Suppose that is 0.25 for our example. Then after the projection, you end up with 250 pages, right? So with 20 buffer pages that can sort, you can sort this 250 pages in 2 passes. Okay, that's just a simple calculation given the external sorting we talked before. Okay, so let's assume that is true. Then what's the total cost of executing this code? First, you need to read in 1,000 pages from the beta heap file. Then you write them to the disk with only the projected columns. Then you do the external sorting. Finally, you read in this 250 pages with to feed them into the distinct operator, right, to perform the final step. Then finally, you get 2,500 IOs total. And in the next lecture, we will show how you can actually reduce this number to lower. So let's call it this. Oh, please hand in the papers. You have taken them?
So, tomorrow, get into it.
Oh, sorry. Yes. Tomorrow I have to do
That doesn't look too bad.
So, so what text just takes yeah, so it doesn't make any changes. Right. Everything is made by
Do you have this architecture?
So it's about how to keep state across and it's not bad. It's not bad. I'm always happy. And I like networking. So it's kind of interesting. And it's definitely one
Right.
that I there's like you do projects. So you
I might swap
it's not
Try to make it fix semester classes.
I don't know if he teaches
Looks like, yeah, not for most of them are talking.
yeah. I think he's teaching OS, so I might take that because I think he's
I'm taking a lesson.
back to this side. If I take it, yeah, talk to him. I just don't want to do it.
Right. Oh, you have class? How many? You want to just let me know.
I texted you.